There are some important outcomes from Einstein's theories. One of the outcomes associated with his theory of special relativity is the fact that the mass of an object, now how much something weighs is different than its mass, but the mass of an object actually changes with how fast it's going. And the way this works is the faster it's going, the more massive it is. And I know that's strange, but that's true. Remember, this is at extreme speeds. So this is actually showing you the mass of the small particle, and v is how fast it's going, and c is the speed of light. So right here it's going half the speed of light, here it's going 80% of the speed of light, here it's going 90% of the speed of light, which is really fast. And so here you can actually see what its mass is relative to its original mass. So here its mass relative to its original mass stays about the same. Here going about 30% of the speed of light, you start to see its mass kick up. 50% of the speed of light, there you go. Okay, and clear over here, 80% of the speed of light, it weighs about more than 1.6 of what it weighed before when it wasn't moving. So I think that is pretty cool. Mass increases with increasing velocity when you're talking about fractions of the speed of light. Pretty darn fast. With regard to an outcome of his general theory of relativity is this. There are two ways to feel a similar force. One is the force due to a gravitational body, like standing here on Earth, we feel that force. And another is the force due to you are accelerating. So those two forces. And what this is showing you is that this astronaut doesn't know, he feels gravity. Here he's sitting in his little chair waiting to take off. He feels gravity due to the Earth. And here he feels a force due to he is accelerating. Now remember, keep in mind that acceleration means that the velocity is increasing. Velocity is changing is what acceleration is. So he's going faster and faster and faster and faster. And he feels a similar force. And he can't distinguish between the two. I think that's pretty cool. Another outcome of Einstein's theories of relativity is this idea of the fabric of space-time. And actually, this phenomenon of space-time is a player when we start to talk about kind of large-scale objects like galaxies and kind of the fabric of our how our universe is arranged. So what Einstein said, and it's been proven, is that when the entity space and entity time actually create a fabric. And so when we feel gravity, and I'll try to convince you of this, gravity, according to Einstein, and it is consistent with Newton's gravity, obviously, is really just kind of creating a dent in the fabric of space and time. And so actually that has consequences. What you're seeing here is something that's been observed from the planet Mercury. Okay, so Mercury, of course, the closest planet to the sun. Here we're seeing Kepler's laws in place that the orbit of Mercury is kind of oval. We call it an ellipse. And as it turns out, because of the dent that the sun is making in the fabric of space and time, that's actually what causes Mercury to go slows down out here. Okay, that's also one of Kepler's laws of planetary motion. So my point is, based upon this, we would expect that Mercury's orbit can be shifted just ever so slightly. And here we're kind of seeing the shift. This is Mercury orbiting the sun. Mercury orbiting the sun. You can kind of see it's a little bit of moving. Okay, it's about math too. So one more thing, and this is a clear way to look at, do you see the sun kind of making a dent in the fabric of space-time here? Well, it's not just, light. Light can actually be will follow the curve that's made by the sun. So this has actually been observed before. Here we have a star, and this is the star's true position. So the starlight comes here, and we're here. Okay, this is us. The starlight comes here, and you would expect us, if it was normal flat space-time, which is not, you would expect us to see, if the Earth is here, we'll see the star here. But what happens is its light actually gets bent or follows the curved space-time, and then it comes back up out of kind of its little dent, and we see it here. So if you take this trajectory back, where we actually see the position of the star, this is where we see it, okay, and this is where it is. So it's actually that the position is shifted due to the dent that the sun is making in the fabric of space-time.